Thank you very much. And let me also thank the organizers for having me. This is my first in-person talk, so I'm very excited to be here and share with you these recent results that I got with my advisor, Pengzi Miao, regarding Bartnik mass. I had to click. Oh, I got it. All right. Okay, so this is just the structure of the talk. I will start by giving a brief introduction on mass, and then we will start talking about Bartnik mass. And I will outline some of the estimates that are known for the Bartnik mass. And from there, we will move on to our main estimates for today. And I will show you briefly the construction that we use to get to that estimate. And finally, we will talk about a geometric implication. Okay, so mass. In Newtonian gravity, we know that if we want to find the mass of a system, what we can do is take this mass density function rho, and then the mass is just going to be given by integrating over R3 this function rho. Moreover, we know that rho and the gravitational potential are related by the Poisson equation written here on screen. And then assuming some reasonable decay, we can use the divergence theorem to see that the mass can be written as a flux integral at infinity. Okay, so we would like to have a formulation like this also for GR. However, in GR, things are a little trickier. So let me start first by restricting the framework for GR. So to define mass, we need to restrict to a special kind of manifolds called asymptotically flat. Asymptotically flat manifolds physically represent isolated systems in which all the matter is contained in a compact region. And the further away we go from the compact region, the less we're going to feel the gravitational field. And this geometrically will imply that the manifold gets flatter and flatter. So it will get closer to the Euclidean metric. So to make this statement more precise, we can define asymptotically flat manifolds to be manifolds that have coordinate charts outside a compact set, so that the metric G can be written as the Euclidean metric. This is the Euclidean metric plus an error term. And we will also have some control over the derivative of the metric. Moreover, we want to assume that the scalar curvature Rg is integrable, and we will see that that is a condition we need to have so that we can actually define the mass. Okay, so from the point of view of the Cauchy problem in general relativity, we know that we can rewrite the Einstein equation if we have a time symmetric initial data set as a constraint equation that you can see here. This is an equation that relates the scalar curvature Rg with rho, and rho is the mass energy density. However, if we compare this with the Poisson equation we saw before, well, here the metric will play a similar role as did the gravitational potential before. However, rho here does not determine G, right? It will just constrain its scalar curvature. Moreover, what we have on the left-hand side is not in divergence form, so we cannot just turn it into a flux integral as for the Newtonian case. But here is where we can use the fact that we're restricting to asymptotically flat manifolds, because at infinity, our asymptotically flat manifolds is almost Euclidean. And so we can approximate the scalar curvature with its linearization at the Euclidean background metric. And now if we actually do the computation, one can see that this linearization will have this form here. And now this is great, right? Because we have the Laplacian and a divergence. So this right-hand side is in divergence form. So we can repeat the construction from before to write the mass as a flux integral. This mass as a name is called the ADM mass. ADM from the name of the three physicists that introduced it first, Arnold, Dazen, and Misner. And I should also point out that this is not the original derivation that they had, but this is, I think, a nice parallel between the Newtonian case and GR. So we actually use the divergence theorem. Now we can define the mass in the following sense. It will be, again, a flux integral at infinity, as R here is just a large sphere. And so the first line is just the divergence theorem straight away from what we saw before. However, the most known form for the ADM mass that I'm sure that everyone has seen before. And this depends on the coordinates. However, it was shown by Bartnik and by Crucial independently that the mass is a geometric invariant. So it does not depend on the choice of this asymptotically flat coordinates. Possibly one of the most important results regarding mass is the positive mass theorem. Here I stated for n dimensions. So if we have a complete asymptotically flat manifold with no negative scalar curvature Rg, then the mass is non-negative, and we will have rigidity if and only if we are isometric to the Euclidean space. And if you're wondering what is the significance of this condition on the scalar curvature up here, well, if you remember the equation I showed before, the constraint equation, in this initial data, time symmetric initial data set situation, we know that having no negative scalar curvature is the same as the dominant energy condition, so that we have that this mass energy density is non-negative. The positive mass theorem was first proved in dimension 3 by Schoen and Yao and by Witten, and it was generalized for higher dimensions up to 7 right after, and then recently in any dimensions by Schoen and Yao and by Low-Camp. Another very interesting result regarding the mass is the Riemannian-Penrose inequality. So the Riemannian-Penrose inequality physically states that if we have a manifold with the dominant energy condition, so again, no negative scalar curvature that contains black holes, then the mass of this manifold will be bounded below by the mass of the black hole. That can be written in terms of this area of the black holes. So here is the precise statement on screen. If we have an asymptotically flat manifold with no negative scalar curvature, so that the boundary is an outermost minimal surface, so it is not enclosed by any other minimal surface, then the mass is bounded below by this quantity here. So like the boundary of the area of the boundary over 16 pi in the square root. Moreover, we have equality only if we are in a Schwarzschild manifold. The Riemannian-Penrose inequality was proved by Bray and by Huiskin-Lindmannen. Okay, so this was just like a very, very brief overview over mass. Again, from a physical perspective, now we're interested into finding a local version of the mass, right? In Newtonian gravity, we know that if we want to find how much mass is contained in a finite region, we can just integrate over rho, right? And you will get the mass. However, in GR, again, we saw that the mass really only makes sense at infinity, right? So finding a local version of the mass is actually harder than in Newtonian gravity. And it also turns out that it's more convenient to work in terms of the geometry of the boundary of the region we are considering. And notions of this sort are called quasi-local mass. There have been many intriguing proposals for quasi-local mass, for example, by Hawking, by Brown-York, and by Wang Yao. And in this talk, we will in particular look at the quasi-local mass proposed by Bartnik. So let me give you the framework. So if we have a triple that consists of a close connected orientable surface with a metric on it and a function, we call that the Bartnik data. For the Bartnik data, we can define the Bartnik mass. The Bartnik mass is defined as the infimum over the mass. Here, this is just the 80m mass of mg, where mg belongs to this set here that is called the set of all admissible extensions for sigma. And we require mg to be asymptotically flat with no negative scalar curvature. We want the boundary of M to be isometric to sigma and gamma and to have the mean curvature to agree. And finally, we want to have some non-degeneracy condition that will prevent the mass from being made arbitrarily small. For example, that it is outer minimizing or that it doesn't contain any other minimal surface. Here, I'm not actually choosing any non-degeneracy condition because our construction that we're gonna see later, and any of these two conditions will hold. So we don't have to restrict to either. Okay. Again, remember that we're interested from a physical perspective, at least, in how much mass is contained in this finite region. So it makes sense to assume that we have a non-negative scalar curvature fill-in. Okay, but what is it? So we have the sigma, right? We can imagine to find a compact 3 manifold with no negative scalar curvature, and we require the boundary to be isometric to sigma. So the picture will be something of this sort. We have omega, and the boundary will be isometric to sigma gamma, and it will have the same mean curvature. So again, this from a physical perspective, I think is something that makes sense. Moreover, the existence of this non-negative scalar curvature fill-in, when combined with the positive mass theorem with corners, then implies that the Bartnik mass will be non-negative. And of course, this is from a physical perspective, a desirable property for the mass. Okay, now we saw from the definition that the Bartnik mass is pretty hard to compute because we need to find any possible extension and then minimize over the mass of all of them. So finding the exact value of the Bartnik mass is really complicated. However, from the definition, we see that if we can find such an extension and we can compute the mass of this extension, then that mass will be bounding the Bartnik mass by definition. So a lot of work has been done in this sense to construct such an admissible extension, compute its mass, and find some upper estimate for the Bartnik data. An estimate of this kind was proven by Mantoulidis and Schoen for the horizon case, so when h is equal to 0. What they were able to show is that if we assume that the first eigenvalue of this operator here, this is just a Laplace Beltrami operator, this is the Gauss curvature. If we assume that that is positive, then the Bartnik mass is bounded above by this quantity that, if you remember, is the same that appeared in the Riemannian-Penrose inequality and can also be seen as like 1/2 the area radius of sigma. Okay, and in case you're wondering about this condition on lambda, it turns out that in GR, apparent horizons can be described as stable minimal surfaces. And from stability, we will know already that this operator is non-negative. And so the only relevant case that is left out here is the equality case that was actually proven later, and I will make a comment about it. But this estimate from Mantoulidis and Schoen, combined with the proof of the Riemannian-Penrose inequality, shows that we actually can compute the Bartnik mass for this horizon case. So when h is equal to 0, we do have a quantity for the Bartnik mass. We do know the value of the Bartnik mass. Some other upper estimates for the Bartnik mass were given later. For example, Schoen and Martens in 2020, they showed that when that first eigenvalue is equal to 0, the same estimate from Schoen and Mantoulidis still holds. Moreover, a lot of work has been done for CMC. So whenever we have constant mean curvature, for example, by Lin and Sormani, by Cabrera, Pacheco, Cederbaum, McCormick, and Miao, by Miao, Wang, and Shi, and Schoen and Martens. And then Miao and Shi, in case the data has positive Gauss curvature, they were able to obtain the same estimate by constructing an extension of vanishing scalar curvature. Another very important estimate for the Bartnik mass was obtained by Shi and Tam in the case of positive Gauss curvature and positive mean curvature. So suppose that we have Bartnik data where, again, the Gauss and mean curvature are both positive, then the Bartnik mass is bounded above by 1/8 pi, the total mean curvature of sigma when isometrically embedded in R3 minus the total mean curvature H. And since their construction will be relevant for our construction that I'm going to show later, I will just give you a very rough idea of how their construction works. Okay, so I will leave out all the details, but just to give you an overview. Okay, Now, we know that the Gauss curvature is positive. So from the solution to the Weil problem, we know that sigma can be isometrically embedded into R3 as a strictly convex surface. Now, on the external region in R3, we can write the Euclidean metric as d rho squared plus g rho, where g rho will just be the induced metric on sigma rho S, so it would just be the surface the distance rho from sigma. What they show then is that we can find a function u so that this metric gu, defined just by introducing this u squared term here in front, will have vanishing scalar curvature, will be asymptotically flat, and the mean curvature of this will agree with the mean curvature h. Moreover, they were able to show that such function u has the following asymptotic expansion for a constant m. With that, they showed that the mass of this extension is exactly m, and that this extension constructed like this is an admissible extension because it's foliated by positive mean curvature surfaces. And so finally, they proved that this quantity here, so this is h0, again, it's just the mean curvature of the embedding, hu is just the mean curvature of these spheres with respect to the metric gu. This quantity is monotone non-increasing, and at infinity, when divided by 8 pi, will give us the mass. And now we have found a value for the mass of this extension, right? So by definition, this will provide an upper estimate for the Bartnik mass. And finally, since this quantity is monotone non-increasing, right, it will have its maximum at sigma, and we saw that the mean curvature will agree with h. And this is their construction. Again, just I left out all the details, but just to give an idea. Okay. Another estimate for the Bartnik mass was provided by Miao. So remember how Mantoulidis and Schoen were looking at this extreme case of the horizon, so where the mean curvature vanishes. Miao instead looked at another extreme case of having the metric to be the round metric, okay, and then h to be a function that is positive on sigma. What it was able to show is that the Bartnik mass is bounded above by this quantity that you see here. This is the bound from Mantoulidis and Schoen, right? This is the 1/2 area radius. And then we have this quantity here that if you're familiar with the Hawking mass, this almost resembles the Hawking mass, right? Up to the fact that Hawking mass will have h squared. And here we're squaring the total mean curvature, okay? A nice feature of this estimate is that you see, if the mean curvature or the total mean curvature here approaches 0, then this term will vanish, right? So this will be gone, and we will again get the estimate by Schoen and Mantoulidis, which is something that is desirable, right? Because we do know that when h is equal to 0, the Bartnik mass is exactly that. While if we look back at the estimate from Xi and Tam, when h approaches 0, right, or the total mean curvature approaches 0, then we will get this term here, right? And using the Minkowski inequality, this will actually be bigger than the area radius. So we will be a little further from the optimal estimate. Okay, now here I just rewrote Miao's estimate in terms of this area radius that is just defined by the area divided by 4 pi and the square root. And what Miao showed is that this estimate is optimal in the following sense. So when h is a constant, then, well, if h is a constant, then this term here will exactly be the term that appears in the Hawking mass, right? Because squaring the total mean curvature, just squaring h, will be like the same, up to the fact that we're dividing by the area. But we will get exactly the right-hand side to be the same as the Hawking mass. And remember that here we're just taking the metric to be the round metric. And so we know that in that case, the Bartnik mass and the Hawking mass agree. And so in this sense, we will get the equal sign. This is because it's like having like a sphere in Schwarzschild, right? In Schwarzschild, we know that we have that the Bartnik mass and the Hawking mass agree with the parameter m. And so we have the equality sign. Moreover, if we compare this with the Xi-Tam estimate, we will have that this right-hand side here is strictly less than the bound from Xi and Tam, unless the total mean curvature is 8 pi r, right? And this condition, if we are assuming that a non-negative scalar curvature field-in exists, this is the same as from Xi and Tam result, actually, as our data arising from a ball in R3, a standard ball in R3. So in this sense, Miao proved that this estimate is optimal. Okay, now we're gonna move to our new estimate that can be seen as a generalization of Miao's estimate. Yes. Could you just explain the second bullet point again? Sure. Okay, so this actually is kind of like simple to prove because when we are, this is a round metric, right? So H0 will just be 2 over R, right? The error radius. And so you can actually rewrite this whole term as like, it will be like a quadratic, sorry, like something squared with equality only when we have this. Okay, so that's where it follows. Let me think. Well, if we have, well, that will come from Xi-Tam, I guess, right? So if we have a non-negative scalar curvature fill in, then the total mean curvature will be less than the integral of H0. Yeah, we are assuming that H is positive. It is an assumption. Well, then we wouldn't really have this estimate, right? Like it is needed to assume that H is positive for this to be true. There is, should I look at the chat? Oh, the last inequality, okay. All right. Okay. All right, thank you. Right. So I hope that that explained it. Okay. Right, so this is our estimate now. Now we don't need to consider round metric anymore. We can just take any metric on sigma. We are assuming again that the mean curvature is positive and that the Gauss curvature is non-negative. Then in this case, the Bartnik mass is bounded above by this right-hand side here. Okay, so let me make a couple of comments on these estimates. First, notice that we get the total mean curvature appearing here, and each time we're dividing by R gamma, right? This means that this quantity here in the parentheses is scaling invariant, right? Because we're dividing by the radius. And so we will like this zeta gamma that appears here to also be a scaling invariant quantity so that this whole bracket will be scaling invariant. And we can do that. Moreover, zeta gamma is a quantity, I will talk about it more later, but what we know about it is that when we take the round metric, it will be 0. It implies that this term will vanish, right? And we recover exactly the Miao's estimate I showed before. So in this sense, this is a generalization of what we saw before. And then when the Gauss curvature is close to the Euclidean Gauss curvature, then this will go to 0. Okay, now a couple of remarks. So here's the formula again. Now consider again the case in which the total mean curvature goes to 0, right? What will happen? This term will be gone, this term will be gone, right? So the whole bracket will just be 1. So we do recover the horizon came from the Mantoulidis and Schoen estimate. Moreover, the construction that we use does not require the use of isometric embeddings. However, the price we pay for that is this quantity zeta gamma. Because zeta gamma, we saw in the previous slide, that will go to 0 whenever the metric is close to the round metric. However, if it's not close to the round metric, this potentially could get very big, and that will make the estimate pretty rough. Okay, so in that sense, this is the only drawback of this estimate. Okay, so now I'm gonna present the construction. Of course.
So that thing is about, can you also just think of this data as just being a function of the ratio?
So I'm gonna talk about it like in details when we go into the construction. In fact, in the first part of the construction, I will just show how to get the estimate like shown here, and then I will take some time to actually look at this quantity here and look at what kind of estimate we can get for this zeta gamma function. First, we will get estimates in terms of the conformal factor using the uniformization theorem. And then using some PDE results, we can actually see how this condition will imply that this zeta gamma function goes to 0. But I will talk more about it later. Yes. 3 dimensions, yeah. There is, but I will not present it here because, I mean, to me at least, the Bartnik mass makes more sense in the 3-dimensional case, like the physical relevant case. But at least for the estimate for this part, we do have like a higher dimension analog. But this part is actually just 2-dimensional, like this consideration of zeta gamma. Yes, because we're using a Sheetam construction that requires H to be positive. I'm not sure about that. Okay. So to the construction, okay? So inspired by the construction of Mantoulidis and Schoen, we start with a smooth path of metrics that will satisfy the following condition. So we have a path of metrics that will connect our metric gamma to a round metric. And we assume that this path as positive scalar curve, as positive Gauss curvature here, and that we want to have this condition that the trace of this gamma prime of the derivative of this path vanishes for any t. Now, also for simplicity, we're going to do this construction when the area is normalized for 4 pi, and then just using a rescaling argument, one can have it for any radius. Okay, now we consider a real parameterization. Let me actually sketch it real briefly. So t is the parameter of our path of metrics. So we're going to consider a new function that depends on s, so that t of 1 is equal to 0. Then there is an s tilde, for which t of s tilde is equal to 1. So this is 1 is t. And after that, it's constant 1. And then we just have any reparameterization here. So this is the function we're considering. Now we can define this metric gamma s to be gamma of t of s, and then we can define a metric on 1 to infinity cross sigma to be this g bar metric here. And an interesting feature of this is that, remember, when s is bigger than s tilde, this is identically 1, right? So gamma s is gamma of t of s here, right? So when s is bigger than s tilde, this is just gamma of 1. But our path of matrix is connecting to the standard round metric, right? That means that for s bigger than s tilde, this is just the Euclidean metric. Now for this, we can use Sheetam proof, so we can find again this function u, so that we can define this new metric g that will depend on u, so that this metric has 0 scalar curvature. The mean curvature of sigma 1, so of the level set 1, agrees with h, and that this is asymptotically flat. So here's where we use Sheetam's construction. Okay, now the main ingredient to get to our estimate is the following lemma. Okay, of course. That's a good question, actually. That is to have control of the mean curvature. So if we assume that the trace of gamma prime disappears, then the mean curvature will be 2 over s. So it will be the same as in the Euclidean case. All right. So now, if we define these quantities alpha and beta that depend on the mass, on the path, sorry, alpha will be the maximum of the derivative of the norm of the derivative, and beta is just the minimal Gauss curvature of each slice. Thank you. What one can prove is that if we define this script h to be the total mean curvature over 8 pi, okay, here hs is just the mean curvature of this sigma s level set, then when we take the derivative of this quantity squared, it will be bounded below by this quantity that depends on alpha s and beta of s. There are these alpha and beta under the reparameterization that we saw before. And this is actually just a straightforward computation starting from Gauss equation and just using the metric that I showed before. Okay. Moreover, from Shi and Tam, we know that the total mean curvature will have this asymptotic expansion here. And so in the total mean curvature, we can read the mass, right? And so we can use the inequality I showed before, the lemma, to get an estimate for m, for the mass of this extension. And if you do the computation, here is actually just like ODE kind of techniques, we will get this bound. And since we have a bound for the ADM mass, that will provide a bound for the Bartnik mass. And now we can use the smoothing argument. Since t here appears only with this first derivative, one can show that it is enough to start with a function t of s that is just c1, right? So instead of taking this whole thing, we can just concentrate on this part, right, for t of s, and just take a c1 function, and then we can use a smoothing argument to show that the same estimate will follow. Moreover, if we assume at this stage that t of s is monotone, t of s will be invertible. So we can rewrite this estimate in terms of the inverse, that is s of t. And this is our main proposition. If we have a path of metrics as above, and we give any c1 function so that s of 0 is 1, so that it will be the inverse, right? And it's increasing, then Bartnik mass is bounded above by this quantity. And notice how this estimate depends on alpha and beta, right? Those are quantities defined on the path, and then on this s of t. But s of t here is just a parameter, so it's something that we can choose. So in principle, right, we are interested in finding like an optimal bound, so we will want this right-hand side to be the smallest possible. However, minimizing over all possible choices of s of t is actually a very tricky question. We have spent a lot of time trying to just minimize the right-hand side, but we weren't really able to do it. So we do not know how to find an infimum. So instead of doing that, what we can do is just find a good choice of s of t and see what happens then. And this is what we did. Okay. Now, to find a choice of s of t, we look at this middle term of this estimate here. Okay. So we looked at the following ODE. Now, k here is just a parameter, so we can ignore that. We have beta s prime, that is exactly what appeared here, right? It's the numerator of this. And we're setting that equal to, up to a parameter, alpha s over s prime. But alpha s over s prime is exactly the derivative of this exponential function. Okay, so basically, when we consider that ODE, if we have a solution of it that is s of t, then this integral here will just be the derivative of this exponential function, right? Because the top will be the same as this exponent. And so we can integrate it. And so if we assume this condition on alpha over beta, that it is L1, we can solve this equation 6, and we will get the following solution for s of t that again depends on the parameter k. And when you plug this back into the estimate, there is like a natural choice for k, for which the estimate will look like this. And now you see that all these quantities just depend on sigma, right? Up to this integral up here, that is the one that depends on the path. And so again, we want to find the best estimate possible. So we can just take the infimum of that. If we have the infimum over all possible paths, right? All the rest does not depend on the path. Here we can construct many other paths and we can just take the infimum of this quantity. And if we do that, we will get like the best estimate out of this. Okay, and now up to our scaling argument, we will get the main estimate that I showed before. And from this, you can see also the round case. Okay, so zeta gamma is this integral here defined over alpha and beta. Now, suppose that we have a round metric. Remember that our path of metrics is connecting gamma to the round metric. So when we start with the round metric, we can just take the constant path, right? But now alpha is a quantity that depends on the derivative of this path. But if the path is constant, alpha will be 0. So when we have a constant path, this alpha will be 0, and so this infimum will be 0. So this show that for the round case, this estimate is the same as the one derived by Miao. Okay, but now again, we want to try to understand this zeta gamma better. So this will be the second part of the proof. Because here now we're in 2 dimensions, so we can use the uniformization theorem and construct this path more explicitly. Okay, so by uniformization, we know that gamma can be written as a factor times the round metric. And so, inspired by the construction by Mantoulidis and Schoen, actually using their results, we can define a new path of metric, new path of metrics that will look like this. Here we have 1 minus t, so that at t equals 0, we will get gamma. At t equals 1, we will get the round metric. And then we have this quantity here that is just to normalize the area. We want the area to be normalized because you see, remember that the third condition that we have of the path of metrics is that it has this vanishing trace, right? But this path doesn't necessarily have that condition. So we want to revise this into a path that has a vanishing trace for gamma prime. And we can do that using a construction for Mantoulidis and Schoen using a 1 parameter family of diffeomorphisms. So if we do that, assuming that this path is with constant area, we can actually just revise it into a new path gamma of t. Now we have this path more explicitly than before, right? So we can compute alpha and beta in terms of phi, right? Alpha and beta, again, are just quantity that depends on the path. Just alpha is the norm of the metric, beta is just the minimum of each slide of the Gauss curvature of these slides. If we do that, also making use of Gauss 1a, so this is also why this is now specific for 2 dimensions, we will get the following bound for this quantity. Remember, this quantity was the one that appeared in zeta gamma. And here it will all depend on different norms of phi. And these norms appear from using PDE estimates. Because remember that if it was just simple, this path, it will be better. But of course, since we have revised it into this new path, right, we will have a diffeomorphism or a pullback, right? And so when we compute this alpha and beta, this will all depend on a PDE. And so we would have to use PDE estimates to get to this. Okay. But now we can take this a step further because we know that from just conformal geometry that the conformal factor and the Gauss curvature are related by this PDE here. And this is a very well-known PDE in the frame of prescribing scalar curvature, right? The problem of prescribing scalar curvature. And so there has been a lot of work done that we can use. In particular, when the Gauss curvature now is strictly positive and it is close to 1 in the C0 norm, we know from the work by Chang and Yang and by Xing Guangbu that under a balancing condition, the C2 alpha norm of phi will be bounded above by this quantity. This is just like an absolute constant. And this is the Gauss curvature -1 and the C0 alpha norm of it. And we can make this assumption here because Chen and Yang, they showed that we can always find a conformal factor that will obey this condition just by taking a diffeomorphism. And since our construction is true for any conformal factor, we can just start with a conformal factor that will obey this. And so this is okay. And finally, we want this to be scaling invariant, so we can just rewrite this in terms of this pinch of the maximum over the minimum of the Gauss curvature. And that will imply that our bound for this integral of alpha over beta is bounded by this quantity here. And now from this, we see that whenever this quotient approaches 1, so whenever we're close to the Euclidean metric, this right-hand side will get to 0. And so the zeta gamma that was defined over the infimum of this quantity will get to 0. I guess that it will be enough to just take the supremum. Yeah. Well, hold on. This is the maximum over K, right? So yes, so we do have, yeah, right. Yeah, so probably in this case, it's just enough to take the absolute value. Yeah, that makes sense. All right. And now we can see an application of our estimate here in this context of body surroundings horizons. So now, assume that we are in the setting in which the Riemann-Penrose inequality holds. So we have some minimal boundary, sigma h, and we have this asymptotically flat manifold with no negative scalar curvature on it. So we know by the Riemann-Penrose inequality that if this is outermost, of course, the mass of this extension will be bounded by this area of the horizons. But now we can use our estimate to get to like a localized version of the Riemann-Penrose inequality. So let me explain what I mean here. Suppose that we have here another surface sigma that will obey the assumptions for our estimate for the Bartnik mass. So assumption I there. Then we can consider this bounded region here, omega, right? And combining this estimates that we had before with the Riemann-Penrose inequality, we can show that this estimate here is true. And you see that this right-hand side now just depends on the geometry of this sigma instead of like the geometry at infinity. And so in this sense, this application can be seen as a localization of the Riemann-Penrose inequality. Okay, and so this is what I wanted to talk about today. So thank you for your attention.